Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we're going to learn all about alkanes. And we're going to start with how to name them and writing their empirical formulas. So I'm going to start with how we name an organic compound. And I'm going to start with this picture on the left. The picture on the left and the picture on the right are actually the exact same compound, just in two different formats. So in our previous lesson, we looked at different ways of communicating chemical compounds in organic chemistry. The one on the left is called a line diagram, and the one on the right is called a ball and stick diagram, which is actually what a molecular model kit would look like if you were to build it. Both of these are necessary to understand, and so we're going to go through them. The first step in naming any organic compound, especially hydrocarbons, is to find the longest continuous chain of carbons. Now, looking down here, I just want to quickly review that every end of a line or vertex would represent a carbon in this compound. And so those would be all of our carbons. And on this ball and stick, these black balls on this diagram, the center balls would all be carbons here. And all of the little white spheres on the outside represent hydrogens. So I know that on every carbon here, it's maxed out, it's a bonding 100%. There is enough hydrogens to make 4 bonds for each carbon. But we're not going to draw those in because we'll be able to figure that out on our own at the end. So now that I've labeled where all the carbons are, I'm going to find my longest continuous line, and I like to highlight it. So a longest continuous line can zig up and down, it can move around, but what it can't do is go back across a line, okay? So for this one on the left, it's pretty straightforward. We kind of have 3 options of where we could go with our longest continuous line. We could start here and go down here. There's only 4 carbons there though. So that's one option. I could start on this end and go down like this. That would be 1, 2, 3, 4, 5, 6 carbons. Or I could just do the line straight across, and I would have a total of 1, 2, 3, 4, 5, 6, 7 carbons. So I'm going to highlight that longest continuous line. This is called my parent chain, and it's going to have my root word or the root number of carbons in it. So let's talk about these root words. If I have 1 carbon, it's called meth. So methane would have 1 carbon in it. If I had 2 carbons, it's eth. Ethane would have 2. If it's 3, it's called prop. Propane has 3 carbons in the main chain. 4 is bute, like butane. And then after this, you have all your common shape names from mathematics. So 5 would be pent, like pentagon. 6 is hex. 7 is hept. 8 is oct. 9 is non. And 10 is dec. Most students know 5 through 10, and in our course, the maximum number of carbons allowed in the main chain is 10, so we don't have to go past this point. So the root of my name for this compound is then going to be 7, which is hept. That's the root of the name. Now, the suffix or ending of a name tells us something really unique about the compound, whether it has single bonds, double bonds, triple bonds, maybe an alcohol group or carboxylic group. Because all of these carbons are bonded with single bonds and there is no additional functional group, The suffix to this name would be ane. So this is the suffix. And for all alkanes, we're going to end with ane, which means that it's a saturated hydrocarbon, which has nothing but carbon-carbon single bonds. So this really takes care of this part of the molecule. Okay, so there's 7, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7 carbons. That's hept. It's all single bonds, ane, but we haven't dealt with this additional carbon. This additional carbon would be a side group or a branch more specifically. We would call this a branch because this is made of carbons and hydrogens. Now we're still actually going to use a root word here to describe the branch. The branch is always going to be a prefix on the name, and you should know that pre means at the start of a name. So this is going to go in the space in front of the hept. Now, because it's one carbon, it would be meth, but because it's a branch, branches end in a YL. So this is actually called a methyl group or a methyl branch, and that's going to run right into the word heptane. So this is methyl heptane, but we're not quite finished yet. I could have the methyl group here on this carbon, but I technically could have it here, or I could have it here. Now, because of that, I have to give it a location in order to explain where the methyl group belongs. So, since it's on the 1, 2, 3, third carbon, this is going to be called 3-methyl heptane, this being the location on the main or parent chain. Now, a common question is always, well, can I start from the other end? The answer is yes, except not in this circumstance. If I start on the right, I would go 1, 2, 3, 4, 5, and this would be called 5-methyl heptane. However, based on rules, we always have to keep the number of the first branch or side group as low as possible. So numbering it from left to right, I have a 3, which keeps the numbering as low as possible. If I went from this side, it would be 5-methyl, and that's considered incorrect. So this is the exact same name here. This would be called 3-methyl heptane. It's just a different diagram of the same molecule. So let's look at our next one. Our next one, if I look, the longest continuous chain seems to be the one right through the middle, like this. And what I always like to do is put the carbons in on the chain because it makes it easier to count. So if I notice, I've got 1, 2, 3, 4, 5, 6, 7, 8 in the main parent chain. And I also have 2 branches. So this is a branch and this is a branch as well. But let's start with the root of our name. So 1, 2, 3, 4, 5, 6, 7, 8 is oct. Octane because there are all single bonds. Oct because there are 8 carbons in the parent chain. So my root is oct for the main parent chain. My suffix is ane because I have nothing but single bonds. And so the next thing I need to do is deal with the 2 branches. The branch to the top here has 1 carbon, and so this would be called a methyl group. And the branch to the bottom has 2 carbons, so 2 carbons in organic chemistry is eth, so this would be an ethyl group. Now I do need to number them to keep the first branch as low as possible. So if I was to start numbering the carbons on the left, it would be 1, 2, 3, 4, 5. It would be 5-ethyl, 6-methyl. But if I started on the right and I went back the other way, this would be 1, 2, 3-methyl, 4-ethyl. Now that keeps the numbering to as low as possible. So I know that this is a 3-methyl and this is a 4-ethyl. But I have to make sure that I put them in the correct order in the prefix position in front of octane. I can't just choose whichever one I want to go first. I can't say it's 3-methyl or it's 4-ethyl and then the other one. There is a specific set of rules that you have to follow with prefixes, which are below here. It says prefixes are always ordered alphabetically if there is more than one of them. So what I've done here is I've included a bunch of different prefixes we may come across in this course, and I've ordered them in alphabetical order. So for instance, if I did have a bromine, it would go bromo first. A butyl group would have 4 carbons. Chlorine, chloral group. The first one we hit that we come across a lot is ethyl. Ethyl, E comes before M, methyl. And so when I write the name, ethyl has to go first. So this would be called 4-ethyl. The dash always goes between a number and a word. Then it would be dash, 3 dash, and then I would have my methyl, octane. So to be clear, with my prefix, it has to go alphabetical, not numerical, although sometimes that happens naturally. The E has to come before the M. It's not the 3 have to come before the 4. It's based on the names of the branches. So please make sure that you memorize that the prefixes must go in alphabetical order no matter what, not necessarily numerical order, which this one doesn't. 4 is a larger number than 3, but I don't care. Now I do want to point out one thing down here. If theoretically I had 2 ethyl groups or 2 methyl groups, it would be called dimethyl or diethyl. These dis or tris or tetra, if I had 4 of them, does not affect the alphabetical order. So for example, if you look here, I've got a compound and it's called 4-ethyl 3,5-dimethyl nonane. Now I'll show you what that would look like. Here's nonane. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. What this would look like is on the 3rd carbon, I would have a methyl group. There's a methyl. On the 5th carbon, I'd have a methyl group. There it is there. And on the 4th, I would have an ethyl, which would look like this. This would be a methyl group, and an ethyl group. Now, because there's 2 methyl groups, it has to be called dimethyl, and I have to number where both of them are. Now, D in the di technically comes before E in ethyl. However, the rule states that the addition of a di or tri to the naming system does not alter where they fall on this series. So even though dimethyl, which starts with a D and D comes before E, when I write the name, the methyl still has to come after ethyl. So it is critical that you remember when you do prefixes, they must go in this order, even if there is a di or tri associated with one of the branches or functional groups. The last thing I want to do before we move on from this page is talk about how do I figure out the molecular formula. Now, some people call it empirical formula, or tests will. But basically, I'm trying to figure out how many carbons and hydrogens are actually in this compound. So, the first thing I would do here is I would check to see if it's an ane, ene, or ine. And in our previous lesson, we learned that anes have this generic formula, CnH2n plus 2. So what I need to do is first count up the number of carbons and then put that into this equation. So for instance, meth, or methyl, that has 1 carbon in it, and hept has 7 carbons in it, so 1 plus 7 is 8. So for this compound, I know it's C8H2 2 times 8. I'm taking this 8 and putting it there, plus 2. So 2 times 8 is 16, plus another 2 is 18. This would be C8H18, which is just telling me the molecular formula of it, the number of carbons, the number of hydrogens in the compound for either of those two diagrams. So let's do it for the second one. In the second one, I'm also doing an alkane, so it still follows the CnH2n plus 2 formula. I have to count up everything. So down here, eth is 2, meth is 1, and oct is 8. So that's a grand total of 11 carbons. And so this would be C11H2H 2 times 11 plus 2. So 2 times 11 is 22, plus another 2 is 24. This is C11H24. That's how I figure out how many hydrogens are in the compound. I wouldn't actually draw all the hydrogens in and count them up. It's so easy to make a mistake like that. So again, 11 carbons in the compound, 2 times 11 is 22, plus another 2 is now 24. And I figured out the molecular formula. The next compound we're going to look at is 2,3-dimethylhexane, and we're going to look at drawing it in 3 different ways. However, we're first going to start by figuring out its chemical formula. So, because this is an ane, I understand that the formula is going to be CnH2n plus 2. So to figure out the number of carbons, I read the name, dimeth. Meth is 1, but if it's di, that means there's 2 of them. And hex is 6, so that's going to be 8. So this is going to be C8H 2 times 8 plus 2. So 2 times 8 is 16, plus 2 is 18. The chemical formula is C8H18. So we're going to start by drawing the structural formula, which shows all of the bonds and all of the atoms. So I would start with my parent chain, which is hex, and I draw 6 carbons in a row. I would then look to see if there's any branches, and there's 2. There is a methyl group on the second carbon, so I'm going to add 1 carbon to that. And there's a methyl group on the third carbon, I'm going to add 1 carbon to that. I'm then going to make sure that each carbon is bonded 4 times. This ensures that it has enough hydrogens and it's completely saturated. So starting with the first carbon, I can see it's only bonded twice, so it needs 2 more bonds. The next carbon is bonded 3 times, so it only needs 1. This one needs 3 more to make 4, and I keep working down to make sure that every single carbon has been bonded 4 times. And I end up with a picture that looks like this. Now, I'm not going to actually draw in all of the hydrogens. There is a hydrogen at the end of every one of these lines, but it just becomes too cluttered and too hard to read if I draw all of them in. However, I'm going to show you what I do to ensure that I have drawn this correctly. I will mark off 1 hydrogen in a different color, and then I will count up the number of lines coming off the carbons that represent hydrogens in order to see if I've got all 18. So starting on the left, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18, and I've done this right. A condensed structural diagram shows all of the hydrogens bunched up towards the carbons. So for instance, this would be CH3. That would represent this first carbon that has 3 hydrogens, followed by a CH, which represents this carbon here that has 1 hydrogen attached to it. And then I just keep moving down. So I've got a methyl group above, CH3, another CH group to the right with another methyl group on it. And I just keep working my way down using the structural diagram to help me finish off my condensed structural diagram. So I've got 1, 2, 3, 4, 5, 6 in the main chain. I have 2 methyl groups, and I know that every carbon is bonded 4 times based on my previous diagram. The line diagram is the simplest of them all and probably people's most favorite to do. So I would start by moving up and down, making lines until I have 6 carbons. So remember, the end of a line and a vertex each represent a carbon. So I have 1, 2, 3, 4, 5. I need one more. That would be 6. Then I have to add my methyls in at 2 and 3, and my line diagram is complete. The next thing we're going to look at is structural isomers of alkanes. So what an isomer is a compound that has the same chemical formula as another compound, but it looks different. So for instance, our question here says draw 3 structural isomers of pentane. Now pent is 5, so C5. Ane is 2 times that number plus 2. So there's C5H. 2 times 5 is 10 plus 2 is 12. C5H12 is a chemical formula. Now there's more than one chemical compound that has 5 carbons in it and 12 hydrogens in it. We can draw them in different ways. Their structure is different, and so we call them structural isomers. Now, up here, I have a list of conditions to figure out whether you have an isomer of an alkane. So a few things must be true. First of all, it must obey the CnH2n plus 2 formula. There is no loophole to this whatsoever. An isomer of an alkane must have that formula. Other things I'm looking for is there better not be any multiple bonds, so no double bond enes, no double or triple bond ines. It must be a chain, whether it's straight or branched, but it cannot be cyclic, which means in a ring shape, and it definitely can't be benzene, which is also in a ring shape. So if it has none of these things, and it has the same number of carbons as the other structures, if 1, 2, and 3 above are all followed and it has the right number of hydrogens, then we're going to be an isomer. So for instance, let's start with pentane. We're going to do the line diagram. So 1, 2, 3, 4, 5. This is pentane, and it has the formula C5H12. Now, what I would do to figure out an isomer of pentane is I would shorten the main chain by 1 carbon. So for instance, I can make it look like this, which is a butane, and I can move this carbon, which I've taken away from this structure, and move it to the inside to make a branch. So for instance, I could put a methyl group there. So I'd still have my 5 carbons, 1, 2, 3, 4, 5, but my parent chain would be 4 instead of 5, and this would have the name 2-methyl, because there is a methyl group on the second carbon, butane. Now, I don't want you to copy this out. I'm going to show you something that students often do, which is a mistake, is they would draw the same butane, but they move the methyl group down here, and they would call it 3-methyl butane, indicating that the first carbon is carbon 1, this would be carbon 2, this is carbon 3, and this is carbon 4. So again, this would have that C5H12 formula. However, if I'm naming this correctly, I have to label the branch with the lowest possible number, and so I would do that by leaving it this direction. There is no such thing as 3-methylbutane. This is simply 2-methylbutane drawn backwards. So please don't think that if you draw things something one way or the other way, that it's going to be necessarily an isomer. You have to name it after you draw it following the proper rules in order for it to be real. So I don't want to draw that out again because I have it above. So one isomer of pentane is going to be 2-methylbutane. Now, the next thing is I would have to shorten this chain up again. So I can make it into a propane, but then I would have to have 2 methyl groups coming off of it. So there's my propane. I'm gonna highlight it so it's easier to see. This is propane. And then in order to get up to 5, I would need 2 more methyl groups. So I need a methyl group there and a methyl group there. It kind of looks like the letter X. Some people draw it like this. However, most textbooks show it like this. Okay, so I've got 3 carbons in the parent chain, and I've got 2 methyl groups on the second one. So correctly done, this would be 2,2 dimethyl. There's 2 methyl groups on the second carbon, propane. If you work that out, it's still C5H12. And then if you look this up, you may see it without the 2,2 dimethyl written in 2,2 in front, because that's the only place we could put the methyl groups. If I put a methyl group here off of the first carbon and got rid of one of those, this would just become butane again. The only location you could put the methyl groups is on the second carbon, and therefore sometimes they don't write the 2,2 in at the front and rather just call it dimethylpropane. In our next section, we are going to look at chemical and physical properties of alkanes. So, the strongest type of intermolecular force present in any hydrocarbon is always a London dispersion force. There are no dipole-dipole or hydrogen bonding present. So, because of this, it is very insoluble in water due to the fact that water is a polar compound. However, it is highly soluble in other nonpolar compounds, such as if you had hydrocarbons in a barrel of oil, which would be a variety of different types of hydrocarbons of size. This makes it easy to figure out how the melting point and boiling point changes for alkanes. Simply, the bigger the molecule gets, the higher your boiling point is going to be, due to an increased L-dip forces, which is based 100% on the number of electrons inside of the compound. So more electrons, the bigger it is, the bigger the polarization of the electron cloud, and the boiling point increases. So just have a quick look at this chart. As you see, as the number of carbons increases, the value of the boiling point increases as well. I did a little jump here from 5 to 10 just to show how massive a difference it is to go from being 1 carbon methane to 10 carbons decane. It's a difference of over 300 degrees Celsius in terms of boiling point. A general rule I like to keep in mind: at standard conditions, essentially 25 degrees Celsius and an elevation of sea level, an atmosphere of 1 atmosphere, carbons 1 through 4 compounds are going to be gaseous. Carbons 5 up to 18, and this depends on the isomers, but roughly in that area, you are going to be a liquid. And being 19 carbons or more at room temperature, you're going to be a solid. So such as candle wax, paraffin wax, the average size of the molecule is about C25, and so that would fall under a solid hydrocarbon. Or you can think of gasoline, which is a mixture of octanes. Well, more than that, but octane being C8, it's liquid. And then of course propane, which we use for barbecues, or natural gas in our furnaces, C1, C2, C3. Those are all gases at standard conditions. Something you should keep in mind, although it's not a very important detail at this level yet, is this. Melting points and boiling points will decrease with an increase in branching. So for instance, let's say we took something like pentane again. This would have a higher boiling point than our methyl butane, 2-methylbutane, and this would have a higher boiling point than our 2,2-dimethylpropane. So as I move this direction, branching increases. There are more branches, and when I increase the number of branches, I decrease the boiling point. We will be looking at 5 different types of organic reactions throughout the unit: combustion, addition, elimination, substitution, and esterification. Alkanes do 3 of the 5, starting with combustion as being probably the most prominent thing it's used for. So combustion is when hydrocarbon combustion is when a hydrocarbon is burned with oxygen to form carbon dioxide and water, if it's a complete combustion. A complete combustion will only produce carbon dioxide and never carbon monoxide or carbon particulates. This is because it has lots of oxygen to completely burn with the hydrocarbon, forming only carbon dioxide. Now remember, when you have a combustion, if it is an open combustion, you will produce gaseous water, and if it is a closed combustion, you will produce liquid water. The other option is you have an incomplete combustion, which essentially means there is not enough oxygen present during the burning in order to convert all of it into carbon dioxide. In an incomplete combustion, you must have one of these 2, and possibly all 3 of these carbon compounds. So whether it's carbon dioxide and carbon monoxide and carbon particulates, or just carbon monoxide, you have to have one of those 2 at the end. You may have carbon dioxide, you may not. And the same is true about the water. You would have a closed system if it was liquid and an open if it was gas. Most questions really focus on the production of carbon monoxide in an incomplete combustion rather than talking about carbon particulates or carbon dioxide. In most incomplete combustions in real life, you will form all 3 of those, but probably mostly carbon dioxide and carbon monoxide. The second type of reaction that alkanes can participate in is called elimination. In an elimination, you form a carbon-carbon double bond by eliminating hydrogens. Okay, so for instance, if I had something like propane, and I'm going to draw the hydrogens in on here so you can see. This is generally done under really high pressure or with a catalyst, high heat. And what happens is 2 of the hydrogens, I'm going to circle this one and this one, on carbons which are beside each other, actually are removed from the alkane. So they would form a hydrogen molecule, or H2 molecule, and then what would happen is the carbons that lost those would form a double bond between them, essentially forming an alkene. So then that would produce propene, like this. And so now we have a unsaturated hydrocarbon. So this is a saturated hydrocarbon, and this is a unsaturated hydrocarbon. This is an alkane, and we are producing an alkene. So again, when we remove the hydrogen like this is called an elimination reaction. We are eliminating hydrogen. We are forming a multiple bond, an unsaturated compound. Now, the name for this specific one is actually called dehydrogenation. You've probably heard of hydrogenation before, like hydrogenated vegetable oil, margarine. This is dehydrogenated, which is the exact opposite. Rather than adding hydrogens into the double bond, we're eliminating or removing hydrogens, so dehydrogenation of the saturated alkane. The last type of reaction an alkane can be involved in is a substitution. I always like to call substitutions one in, one out reactions. It helps me remember what's going on. And generally in a substitution, you'd be dealing with something called a nucleophile, or something which is really electronegative. So this could be things like an OH. Usually this is not how we would make an alcohol, but things like chlorine, bromine, iodine, or fluorine. And essentially what you would have is a compound. I'm going to start with ethane, which is a saturated alkane. And you would react it with likely a halogen. So let's say we'll use Cl2, and I'll write it as ClCl. And so what would happen is one atom in this small molecule of Cl2, so one of the Cl's, would substitute in and replace one of the hydrogens, and they would come out, leaving you with two new compounds that differ essentially by one atom. So the substitution would happen. So I'm going to say this Cl comes in and this H comes out. And so we would produce a new alkane. This would be a halogenated hydrocarbon because it has a halogen in it now. So it would look like this. And then, of course, you would still have this small molecule, but now I should get a color code date to this, so I'll call it that Cl. And then I'll have an HCl molecule coming out. So for every one molecule of Cl, you could substitute in one Cl atom, but never both, just one. And that's why I call it one in, one out. I am substituting one atom for another. The name of this compound would be chloroethane. Ethane, because there's two carbons, ane because they're single bonds, and chloro because it has a chlorine atom. We're going to talk about how to name this when we get to alkyl halides and halogens in a later episode. And then I have hydrogen chloride as my other byproduct. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.